We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heat map view shows the stability of the selected region and provides region adjustment by directly clicking.
Reservis is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
We demonstrate that people can use the spatial cues available in virtual reality to help them effectively remember and recall scholarly articles. We used a virtual coffee shop and asked participants to remember 4 abstracts from scientific publications, and we termed this method a virtual reality memory palace variant.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
The success of a convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the CNN model is not easy to understand. We're introducing Explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural networks. Using the Explainer, users can progressively explore a single model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
We present Stratigraphics, an approach for designing data.
Hi, my name is Clio Andris, and I'd like to welcome you to IEEE VIS workshop on information visualization, geospatial networks, flows, and movement. The idea from this workshop began last December at the Spatial Data Science Symposium organized by Krzysztof Janowicz in Santa Barbara. Somayeh, Alan, and I were there in the sun and talked about being more involved this year in IEEE VIS to promote cutting-edge geovisualization work, a field in which Alan has made immeasurable contributions in over the past 30+ years. The idea for flow and movement came from Dr. Somayeh Dodge's research, as she's an expert on geospatial movement data, and she's the director of the MOVE Lab at Santa Barbara. And I work on visualizing and analyzing geographic and social conceptual networks at Georgia Tech. We're GI scientists. And we know that this is not a GI science meeting per se, but a VIS meeting. And this is an effort to integrate across disciplines and address challenges. We have faced many visualization challenges in the GeoVis community, and flow data to us is not new. We know from Menard's maps or Waldo Tobler's flow maps that visualizing flows has been a topic of study for quite a long time. But we are faced with larger data sets and more complex problems, and we confront issues yet again. Some pop out for flow data in space especially include the static nature of the nodes, as they are pinned to specific positions in space. And thus, the handy force-directed algorithms that solve edge overlap issues don't work well. We're also faced with issues of thickness being a problem, for example. We have issues of showing non-planarity, that things fly over space that it overlaps with, or that the networks are just conceptual, also not interacting with the space underneath it. And that's not necessarily intuitive when we see flows on a map. We don't know that they're just flying over. We tend to think that they're integrated into the geographic space. We have issues of representing origins and destinations as polygons. It's so much easier to abstract to a centroid, but a point tells a different story. Also, when a line is thicker in just a feature space, it communicates a visual variable of magnitude. In geographic space, it covers up other places, even when we use transparency. And even when we curve edges to avoid it, it can also miscommunicate an actual path. So we have a lot of special spatial problems in flow networks. That's my introduction. I personally would like to thank Somi and Alan, and also my mentor, John Stasko, who originally suggested that the urban planners at Georgia Tech get more involved in this wonderful conference. He also suggested that I teach the InfoVis class in the CS department here, which I do. And according to the TAs, it has a lot of geographic examples. Now let me introduce our keynote speaker, Jeremy White. Jeremy White is a graphics editor at the New York Times and an adjunct professor at Columbia University. He has contributed to a variety of visual projects that have earned several Emmy nominations, a Peabody Award, top honors from the Society of News Design, World Press Photo, and Picture of the Year International. Prior to joining the Times, he created motion, interactive, and print graphics for the company he founded in 1998, Blue Shirt, serving clients such as Toyota, Fiat, Sony, and Microsoft. Jeremy has a BA from the School of Journalism at the University of Montana and an MS in Cartography and Geographic Information Systems from the University of Wisconsin. Please join me in welcoming Jeremy White with his keynote speech. Thank you very much for coming to the MoVIS workshop, and we're delighted that you're here.
Well, thanks very much. Hello, everyone, and thanks for having me. It's great to be here. It's a shame we couldn't meet in person, but we'll make do. And what I'd like to do today is talk about some of the visualizations we put together at the New York Times. And I kind of want to do that through the story of one particular project, and that's how the virus won. There were 6 people working on this. Mostly Derek Watkins was putting the project together. But there were a lot of people behind this. There were many editors, different reporters, and the story went live on June 24th of this year. It's basically a reconstruction of what happened in the early stages of the coronavirus outbreak in the United States. So here you can see we're using these dots to literally represent the number of people that were known to be infected. But what we discovered as we started putting this reconstruct together was that there was so much more that was unknown. So we needed to basically show all of these hidden infections and tie this all together in a way that made sense. And so this presented a number of challenges for us because there was a lot of data to go through, but we also didn't want to leave sort of the thematic narrative that we had put together for this. And you'll see what I mean by that as I go through the slides. So we've used dots before to represent people. And here's a good example from a story back in 2015, where the dots here are a 1-to-1 ratio of the number of people that were killed in the Syrian war. And so there are 200,000 dots here. Each dot represents one person. And it starts to really help to have this kind of visualization when you start comparing the sizes here. So here's 28,000 dots. And anyone that's made a dot density map knows that you can fit a lot of dots in a small space. So doing this 1-to-1 ratio is something that we do very often, and we use it a variety of ways. And we also use that same principle for print. So you see the 15 known cases by mid-February in the US compared to the over 2,000 hidden infections by mid-February. And it's really a powerful way to show the contrast of the small numbers and the large numbers. Now, we use geography in the How the Virus Won project, but you don't necessarily need to. This is one of my favorite representations of people that we've done. This was done by Upshot, and this is basically looking at the resulting income class, the class status of white and black men who grew up wealthy. So basically, chances are, if you grew up wealthy and you're white, you're more likely to be wealthy in adulthood. But I really like the combination of movement and the classification that's happening here. It works really well. You sort of get this metaphor of moving through life and either staying the same or dropping down, and it really, I think, works well. And in the end, you're seeing 10,000 boys growing up to men and seeing where they land in terms of their social class. So pretty effective visualization there. Let's see. Now, we take the reader through the spread of the virus in the US through a couple of different lenses. One important aspect to keep in mind for all of this is how the virus got in the US through the cases that we knew about, but also through these modeled estimates. And so the cases that we knew about were coming in through China. And these modeled estimates have cases coming in from all over the world. So how do we want to show this? How do we show these specific routes, or do we want to show specific routes? Do we make them very general? Do you want to be able to compare locations or compare numbers across all of this? And when we look at this animation, which is something I worked on to show where the estimated cases were coming from, you need to be careful with something like this, because are these great circles? Are they actual flight paths? Are you giving the wrong impression by showing the data in this way? So a lot of considerations to be made. And along the way on creating this particular section of how the virus won, I tried a few things out. How about a point and polygon test? So that basically we're placing a dot inside the state border as it lands. But the problem there is it's very messy. We're trying to strike a balance between showing the general movement and the specific points of entry, but this point and polygon test just wasn't going to do it. It's too tough to read in the end. Also, here's another view. There's too much variation in the starting points of these travelers. So as they come in to the US, it's also very messy. It's very tough to read. Especially when there's motion applied. This is just a still. But using the individual departure airports in this case added an unnecessary level of visual complexity. So another thing we tried is maybe we bring them into the state centroids, and creating these very specific endpoints created these hard patterns, which are very distracting. So this is also something we wanted to avoid. So in the end, we had to come up with a way that conveyed this inflow without showing these visual artifacts. So one way that we've done that in the past is with arrows. We use arrows a lot in the graphics department at the Times. And we use them for different reasons. Here, we're looking at the wind speeds contributing to the California wildfires. And this is from a few years ago. But we can be very literal with these. We can show the direction, we can show the intensity, we can encode many different variables in with each arrow. And this is very helpful for many types of visualization. But sometimes we don't want this. Sometimes we want to use the arrows more metaphorically. But in this case, it really works well to show the intensity and the direction. This is something I worked on years ago. Arrows are very helpful for us for showing general flows. So here the Syrian refugees are getting to Libya and crossing the Mediterranean. But we found out along the way that there were many locations that they were going into, going out of. And this trip to Libya wasn't very straightforward. It had many different locations that we could show them flowing through. And depending on where they were coming from, they used different routes. But we didn't want to show the exact routes because we didn't know them. We knew the city they came from. We knew the city they went to. So another example where you have to be careful to say, oh, these aren't flight paths. These aren't actual routes. But we want to give you a sense of flow and leave a general overall impression. So originally, this was a spreadsheet of city names. But by adding these details, you really start to see how these flows work. Here's a recent example from May showing the most popular destinations for New Yorkers after the coronavirus affected our daily lives, basically. This map could have been made with proportional symbols at each city location. You could scale them proportionally. You would be left with basically the same takeaway, except that the arrows here just give a better sense of movement. You can see where people are going. Here's an example back from 2012. And I thought I'd show this one because these arrows represent attacks on other candidates, and the width of the arrows are the number of words used in those attacks. So here you have the GOP debate. They're attacking each other. They're attacking Obama. So these arrows here are used to show a form of connection, but obviously they're not a geographic flow. So we use them all over the place when we make our graphics and we decide how we're going to show a particular aspect of the data we're working with. So you'll see these used a lot in politics, because you have this shift that's happening. And people are more and more, I think, interested in these shifts because, if elections are close, they really matter. So this story is from 2012, looking back at 2008, and it shows the changing direction and, I guess by proxy, the momentum of these groups as they carried their votes into the election. So this sort of set up what we did later in 2016, where we used arrows to show the shift in the direction of voters' political leanings. This is not, showing any kind of movement in geography, but rather a movement in ideology. So these arrows for us continued to be a very versatile tool. They're not great thematically, however, for the virus story that we put together, because we already had this movement, these dots that we were using. And so to introduce a new element like this, I think it would have been more of a disruptor to the story than providing any more information that we needed. So getting back to the story, let's see. We wanted to look at the estimated number of infections in the early stages. And this is very important, obviously, later, these estimates we see. Early on, we didn't. So by mid-February, we thought that there were very few. Turns out that there were thousands. And by March 1st, it was, even before things started shutting down, the outbreak was here. So there wasn't enough known at that time. And I want to talk about a little bit about how we build these projects, because that's one of the questions we get most often is, how was this done? How do you take a large data set like that? And here you see the movement of people in the first half of March. How do you even visualize this? Because this has to play real time on the web. It has to play on a handheld device, and this whole project is pretty fluid. You can scroll through it. It doesn't stop. You're not pressing a play button or anything like that. So we've used this technique before. This is WebGL. And I actually worked with Derek on a project about Antarctica back in 2017. And for this, we used some custom shaders in WebGL to animate the data. And this is showing the flow of ice based on data collected by teams at Columbia University and elsewhere. But the ice is moving. And this is data that we can track and we can show over time. And they move out over the water and form these ice shelves. Now, this is important to us because as they form these ice shelves, the ice shelves push out into the water, they break. So we're losing a lot of ice floating out to sea. So WebGL was a good solution for this particular project because we could hand off the rendering of the movement of all of the ice to the GPU on the user's computer or handheld device. And we found this technique called color shifting that was used a lot years and years ago for these old 8-bit video games. So you can show movement without the underlying data changing. You're just shifting how it's rendered. So it really starts to make it come alive after a while. So using this color shifting technique, I created these grayscale ramps, and we put these shaders together. And as we were doing this, we discovered that we could control the width, which would then, or the ramp distance, which would then control the speed. And there's a lot we could do with it. So we could show millions of tons of ice moving on a user's, on a reader's phone. So that was pretty exciting for us, but there are some drawbacks. You have to do a lot of testing. WebGL requires a lot more testing than other libraries or other techniques we might use to make graphics. It can be quite time consuming. So before anything goes live, you've got to check it on a number of different devices. Also, things can go wrong. This happened during the construction of How the Virus Won, and these errors and these bugs can be difficult to track down. So things to keep in mind. So we use shaders to move a lot of these dots, and it's in the hundreds of thousands. It varies per screen depending on what we're looking at. If we're looking at the movement across the country or estimated cases, here was the first time we started combining those two things. So we're looking at travel, and we're looking at the estimated number of cases. So we can show where people went, and at that point we have an estimate of how many people were infected as they moved along. So you can see here out of Seattle, any of the red dots that are moving out, that's the percentage of that population moving out of each city that might be infected. So, we're combining a lot of different information here, but we're not leaving that thematic framework that we've set up, which is, we're going to move some dots around. These dots are going to represent different things, but we're not taking you out into showing you some other kind of visual, not a photo, not a video, not some other chart or visual form. So one thing we wanted to look at was New York City, because early on, New York had a lot of cases. So we started collecting data specifically about New York and where New Yorkers were traveling. And a lot of the outbreaks outside of New York were happening because people were leaving New York. And I talked a little bit before about these visualizations and trying to keep the visual form the same, just keeping the story fluid. And even given all of that and trying to keep within this format, we still had to cut some things, which is difficult because these are graphics that we really enjoy looking at and working on, and some of them are very time consuming. So let's see here. We're going to look at New York and some of the local traffic outside of New York up into the Hudson Valley. And that contributed a lot to some of the local outbreaks around New York, but also, down to New Orleans. Mardi Gras ended up being one of these super spreading events. So New York had a role in some of these early events. Now, one thing I want to show here is something that, let's see here, is it not playing? Okay. Here was something that Dawn, who I work with on this project, put together. And this was kind of like a transit map style layout, which made it easy to distinguish the individual routes and the flows. And I really liked this visualization, but it never made it into the final project. It also made it easier to label and to cut down on the feature overlapping. And there's a reason transit maps look the way they do. That layout really helps if you're trying to label a lot and make sure there's not a lot overlapping. But we cut all of it. We cut all of this in the end to maintain a better flow in the story, which is a shame because I really like this. And we also had a series of charts and graphs that we were thinking about using. Here's one of them. Josh Holder, who also worked on the project, started looking at different ways in which we could show the influence of New York early on. So here's one. Here's a scatter plot that he put together. There were also some charts that he put together showing the influence New York had on the outbreaks in other places. So here you're looking at where people came from in different cities, and he had a whole series of these. So we struggled with how to make these points in that thematic visual framework that we had. And sometimes the answer is you just can't. You just can't jump from one form to another, or you have to look for a way to show this kind of information in another way. So, throwing a bar chart in the middle of this story would have, I think, really would have disrupted it. And here's an aspect of the story that I was working on. This is data from NextRain. This is genomic epidemiology of the coronavirus, and this is the North American data. And this is a visualization from the NextRain site. What you're looking at here are what are called clades, and they're categories of mutations of the coronavirus. And these categories of mutations become very important when you're trying to track and go back and show that lineage of the virus over time with a spatial component. So if we know where the virus is coming from, we can look at the strain and see where you see it again and again and again and again and where. But a visualization like this, we're not going to be able to do anything like this for the story that I was showing you. Sure, it's got dots, but it's a whole different way of looking at things. Another visualization from the NextRain site. But a big part of our job as graphics editors at the Times is to reduce the visual complexity of a data set, to really whittle it down into something that is understandable quickly. So I started looking at a few different options. One was just to take the data into D3 and start looking at some comparisons. So here's March 1st and May 1st. You can see on March 1st, there's a lot of fuchsia dots. Those represent the clades, the genetic mutations out of Seattle. On May 1st, you're seeing more of these light blue or teal dots. Those are mutations more closely associated with New York City. So you're seeing that ratio start to change. Started breaking these apart, seeing if splitting them up and showing them side by side would help. So really just started looking at a lot of different ways in which we might be able to work with this. There are also some maps on the NextRange site that you can use to look at the spatial component of this data. But mapping something like this with that level of visual complexity, thematically, it wouldn't work with what we were trying to do because we don't ever really allow the user to explore the data. We're doing the reporting and kind of showing you the results of what we found. So I took some of that data and started playing around with different ideas. And these are just sketches using the real data that we use for reporting and also to help guide the story in the end. So I use proportional symbols here, and you can see San Francisco, Seattle, LA, New York City, and the colors associated with each city, and then basically the outbreaks associated with those locations. So there's a lot of, without even running the analysis, you can see there's a lot of positive spatial autocorrelation here. So, which makes sense. You're going to see something like that when a virus spreads in a location. Nearby locations will likely have the same kind of outcome. I started looking at change over time. So this was just more sketching with the data. And early on, you're seeing a lot of those fuchsia dots up in the upper left, in the northwest. And over time, the more greenish dots associated with New York are showing up more in different locations. One difficult thing with the data, this type of data, is it comes down to sampling. So, if increasing the number of observations certainly helps, but you also need to spread that out spatially in order to get a more robust picture of everything. So in the end, what do we do? Well, as we left New York, as we saw in the previous slide, we start talking more about the genetic data. And so this is where this is what I ended up creating for the clades, the genetic section of the story. So basically, you're looking at Seattle here first, and then all of the other clades are gray. And then we introduced the New York City clades samples by comparison. So you can see these side by side. You can see the difference in size. I think in terms of how the story came together, this is probably a much better way to show some of that data, because all you really want to see is how things changed over time when it came to the spread of the virus. Just as a side note, to make those tiny viruses, I ended up modeling something in 3D and then rendering it with a toon shader so that we could apply it to as WebGL sprites, and so they could render quickly. Doing something like this is a little risky because it can look, you don't want it to look cartoony. You want it to look, you want it to look subtle, but not too overwhelming. So they were smaller, so I think that helped. But there are other times when you may want to use a visual form. Here's a network diagram. You may want to use something like this that is more complex, just to convey the complexity of the underlying data. So there is a video series out right now that the New York Times is doing called the Stressed Election series. And we got some data about Facebook groups and the links to posts online from group members. And so here we're looking at 3 different groups. We're looking at QAnon groups, anti-mask groups, and voter disinformation groups. And so these small clusters represent the online posts associated with those groups. And by spreading these out, and so I just kind of went through and looked at a couple of different ways to look at the network diagram and figure out for this video series, how do we look at this and break it down into its components so that you're not left with just this type of visualization, right? This is difficult to to decipher. So, and often that's true of network diagrams. So first thing I did was just go through each one of the posts and see what these posts had to say. So, but then quickly realize it's not exactly the posts that are the thing we're most interested in here. The most important part here is that these are connected. These are shared. So let's look at the shared post instead of the groups, instead of the entire universe of the post. So this is what ended up happening for the video. And I would recommend anyone go look at the stress election videos. They're great. But and Aaron Bird in video put these graphics together. But basically you're looking at, it's guiding you through each one of the groups, the posts associated with each group, and then it highlights these cross posts or shared content in the network diagram. So in some ways you want to see this complexity, but you really need to push back on some of this. So this last view here, is the most important part. It's this tangle, the bulk of the network diagram is taken away. Like you're getting rid of most of it just to show these shared posts and to show that these three groups are more closely linked than I think most people think. All right, so back to how the virus won. These individual level samples that we were doing at one point, we wanted to take a look at the US as a whole, but then at a certain point, you want to look at individual movement throughout the US. And we had a couple of different examples of this. So let's see. We had one example of someone from New Orleans going to Memphis. So an urban area to an urban area, but we knew that this one 67-year-old woman went to Mardi Gras, then was the likely seed back in Memphis, starting an outbreak there. Then you had someone attending a funeral, going from Atlanta to Albany, and then a lot of the attendants at that funeral also came down with the virus. So, we're looking at a couple urban areas. Here we're looking at someone going home from Tucson to an Indian reservation in a more rural area. And we've seen over time how the Native American reservations have been affected as well. So all of this individual attention is pretty important. And things that we've done in the past, when we're talking about individual movement, when we're talking about flows of people, but we take it down to the individual level, we pair it often with photos. If we can get someone there, if we can get a feel for what's happening on the ground, it certainly helps. So here you're seeing a map of all of these incidents when crossing the Mediterranean by these refugees and the number of dead or missing. But we could have this kind of proportional symbol map, but without these photographs, you really don't get a sense for what's happening or a tone for the story. So, we use these a lot, they help a lot. But we can't always do this. And for the story that we were putting together for the coronavirus, we weren't going to use photographs. But when you get down to the individual level, we use photographs a lot to show this kind of movement. So we do these composites and for the Summer and the Winter Olympics and for other sports too. But and I've been fortunate enough to go there and take some of these photos and take part in this. But it's great to see these world-class athletes performing at their best. And one thing that you can do with these composites is you can take these key moments and annotate what we're seeing. And we do this with a lot of different data, but you're trying to find something interesting here in these time series. So we do these a lot. We build these at the games. It's something that we can do not too long after the event. It takes us a few hours to put these together. But along with some other techniques, it really showcases at the individual level what these athletes are capable of. So we'll select a few athletes ahead of time and do profiles on them, but when we're at the games, we tend to take a lot of these photos. And I wanted to bring this up just because, as you start taking a look at these snapshots, this is something that you can do for an individual athlete, but also for particular data sets where you want to take a look at these snapshots through time. So it's something to consider instead of just showing the flow, is to show where things were at a particular time. It's also nice because you can compare with a relative offset, things happening in the same space, right? So these three skiers did not participate at the same time, but we can go back later and say, where would they have finished? So it's just a nice way to look at some of these relative time offsets. Okay, back to the project. So sometimes you get a data set that really helps summarize what's happening on a larger scale. So Josh Holder got data from a company called Cubic that is basically anonymized cell phone data, and it shows how people limited their physical range after the virus hit. So before the virus started affecting our daily lives, people were moving around pretty freely. And I really like how the movement is used here because it's easy to get a quick impression of what's happening. So you can, as the data changes, you can start to see as the movement goes away, it's easy to see that transition. So here we're seeing after March 17th, things started to slow down, not everywhere. And it started to slow down a lot more in some areas. And the delay in some of the movement here ended up contributing to the larger outbreaks that happened later. So the Bay Area slowed down by mid-March. And you're seeing that happening in some of the more urban areas, including New York. But if we had implemented more restrictions earlier on in some of these locations, especially New York, you would have seen fewer outbreaks. So this was a good way to go through and show what was happening there. Well, you're not able to use this kind of technique for print, for example. And that's one consideration that we have to make at the Times all the time, is that we can create these great online experiences, but when it comes to print, you have to come up with something different because not all of these will translate. So in order to do that, we go back to our good friend arrows. So we'll go back and evaluate a visualization and try and figure out what's the best way to represent that if we're not able to use that same technique. And we can't print that motion on paper and have it translate as well. So here's another example that I just wanted to show briefly. If we're tying a lot of these elements together, here's a serious story from about a year ago. Combines many different types of data. We've got aerial coverage for control areas. We've got discrete locations for military bases. We've got areas of control. But one thing that happens when we start putting together these conflict maps is there's a level of uncertainty that you're dealing with here. And you're trying to combine several different data sets with different levels of uncertainty. And it starts to become difficult. So some things that we do, we'll use arrows, we'll blur lines, we'll fade things out. If we're uncertain about where something's happening, it's better not to show it than to show it and get it wrong. So if you see something that we're doing in the Times and you think, oh, that's an interesting style choice for the way they blurred that particular region, it's probably because we're unsure about the borders or where those lines actually are. And here's one example here, this very large sweeping arrow that comes down to represent the future supply route from Iran to Hezbollah in Lebanon. So here we don't know what the route's going to be, but we're trying to combine it with all this other data and say, there's a lot of uncertainty here, and this is how we're going to show it. And in these conflict areas, and here's a story by Declan Walsh with some photos by Tyler Hicks. These are Houthi rebels fighting coalition forces in Saudi Arabia, fighting Saudi Arabia in northern Yemen. And if we just take a look at Yemen here, it's a rugged country. It's tough to know exactly where the front lines start and stop. And it's tough to know where the control areas are. And you can see the rebels here. We work with the reporters and with domain experts to figure out where some of these borders might be. But I just wanted to show this map that we use for the story, where if you look at the front line, or sort of the middle near the top, you see that fading out. That's because our reporters knew where that front line was closer to the port, but as it went farther away, we didn't know. So we didn't want to, we had a line down as far as the controlled roads, but we didn't want to show it because we were unsure of exactly where it was. You can see some other coalition control areas in here. Those are rather blurry. We did know that the Houthi controlled one road and the coalition controlled another road. And so that was what we ended up showing. And just to end on the last part of the virus story, we struggled a little bit with how to show the end of this story, but because we had data on nursing homes and prisons and general tracking data and meatpacking plants and just outbreaks in different areas. But we felt like the number of lives that could have been potentially saved was the best place to leave it. And then about 36,000 nationwide if we had acted earlier. And then to take a look at the snapshot of new outbreaks across the US, because even then when the project went live, we could tell that after doing all of this research and looking at all of this data, that things were going to get worse before they got better. So that's how we ended this story. Thank you.
Please join me in thanking Jeremy White. That was incredible. Not only timely, but extremely informative from a research and practitioner point of view. We really thank you so much, Jeremy. Fantastic. And we would like to take some questions from the chat. Maybe we have time just for one if there is, as we will need to move to our next speaker eventually. But if there are any, we can take one question. Whoa. Wow, you're getting, that's a lot of applause. You're getting a lot of applause on one. Well, I will ask our brief one question, and then we'll move on to Dipto for his presentation. Jeremy, how do you think that your job would be different if you were conducting it 30 years ago and still working for the New York Times?
Oh, that's a great question. I like that question a lot. I think that, yeah, I think it's difficult these days to, I think it's more difficult these days to be a reporter that is an expert in a particular area. And I think decades ago, we would have relied on that more because there are so many different data sources now that we can easily call upon and get data from. We could just download it. You know, we didn't have to go through lengthy meetings. And I think a lot more was placed on the shoulders of the reporters who had their beat. You know, this is what they were doing. This is they knew who to talk to. And in many ways now, doing our jobs, you know, we're relying on the people who are the experts in these areas. But you know, that means that because we have access to almost everyone now, it seems like everyone's connected, we're able to go to those sources more easily. So I think in some ways it's great to work on this stuff now because we have so many options and so much data, but it can be overwhelming, I will admit. And these days you really have to trust your sources too. So yeah, I think, I don't know that I could have done my job 30 years ago because I rely on the computer so much now. So I think I may not have the skill set back then without the computer to actually pull this off, but it'd be interesting to know and to try. But that's a great question.
Thank you so much. We really appreciate it. Let me just join me in a round of applause, thanking Jeremy one more time, and we will move on with our short papers. Thank you, Jeremy.
Thank you.
Our next speaker is Jorge Wagner.
Hi, I'm George Wagner from the Federal University of Rio Grande do Sul, and I'm happy to present to you our work on visualizing movement trajectories in an immersive space-time cube. One of the reasons we are here today in this workshop is to discuss how new visualization paradigms can help us to better explore the ever-growing amount of human movement data. We believe that immersive analytics offers us a great opportunity to more adequately visualize features and patterns in this data using stereoscopic 3D. Immersive environments also take full advantage of our human cognitive capability through more natural forms of interaction, and they offer unlimited display space and easy support for remote collaboration, something that we all need nowadays. In this project, we are focusing specifically on the case of the space-time cube. As you know, this three-dimensional visualization has a long history, and it employs the third dimension to depict the time component of the data. This way, it can be helpful when we want to analyze features such as the speeds and durations of movements and stops, as well as meetings between different objects. The SDC can be applied in multiple settings, such as in the analysis of human mobility, in sports visualization, in the visualization of vessel navigation, among many others. However, as a 3D visualization, the SDC can be quite challenging, especially when it comes to estimating distances, interacting through 2D devices, and dealing with occlusion and clutter. All of this results in a steep learning curve which hinders its adoption. So my main goal today is to give you an overview of 4 different works we have conducted in recent years on an immersive spacetime cube, and of what we have found out about its usability. I will start out by explaining how we initially validated this concept. Based on our own prior research and the review of a series of SDC applications, we implemented this initial prototype you are seeing based on this virtual desk design. The reasoning behind this design is to allow the data analyst to remain seated in their work desk and to use this desk as a tangible surface for interactions. Mid-air gestures also allow an easier and more intuitive exploration of the data trajectories. We evaluated this prototype in a user study with 24 MoVIS participants, comparing it to a more standard desktop-based implementation. The results from this initial study showed us that the immersive SDC substantially reduced the mental workload and user frustration while increasing its usability over desktop. This VR application also remained comfortable despite over half-an-hour exposure periods, and it stimulated the users to dive inside the data much more than desktop, for example through scaling actions. After this, we have also conducted a series of informal expert evaluation sessions, where we demonstrated this prototype to a series of researchers who had prior experiences with the SDC. We wanted to know how this new experience compared, and obtain feedback based on their actual needs. The feedback we collected in this second study confirmed that immersion minimized typical shortcomings of the SDC. In fact, many of the researchers we interviewed showed interest in applying this new approach to their own data domains. They also offered us a series of suggestions of improvements for new versions, including coordinated views and cutting planes for comparisons, and including advanced filtering mechanisms based on semantic attributes of the data. However, before advancing on this direction, we decided to take a step back and consider alternative navigation techniques beyond the initial virtual desk implementation. To this end, we implemented both exocentric perspectives where the user could walk around the visualization, and egocentric perspectives where the user could walk or even fly inside the visualization. Preliminary findings from this third study show that egocentric exploration reduces the mental workload even further, but exocentric perspectives can improve the performance in some of the tasks. This indicates that when possible we should combine both approaches in the same applications. We have also observed that combining navigation with data manipulation is very important to lower workload and the physical effort of participants. Finally, in our fourth study, we have addressed interaction techniques in the Immersive SDC. We evaluated the two most relevant interactions in VR applications, mid-air gestures with virtual hands and remote selections with virtual pointers. We also offered users a third option which consisted in seamlessly switching between the two modes depending on the actions they wanted to execute. Preliminary findings from this last study show that both virtual hands and virtual pointers are effective means of interaction without any significant differences in terms of performance, workload, or even of the interactivity patterns. Anyway, most participants prefer the ability of combining both depending on their actions in the mixed mode. This mode significantly reduced completion times by up to 23% for the most demanding tasks. However, this came at the cost of a slight decrease in the overall success rates, something that we are now studying how to avoid. So what comes next? Our idea is to extend our visualization and interaction design to support larger-scale real-world datasets, including of different data categories, such as origin, destination, and event datasets. Then we want to conduct more formal evaluations with the data specialists, including by allowing them to explore their own datasets with the system. We also consider it very important to support collaboration in these immersive environments, as collaboration is a fundamental part of many analysts' workflows. Considering the large experience of the MoVIS community, we would also love to hear your feedback. Which features do you think would be relevant to include in an immersive movement visualization? Now, as I mentioned earlier, my intention today was to give you an overview of our works on the Immersive SDC. So I had to skip over many details that some of you are probably wondering about. If that is the case, please don't hesitate to check our publications page. And also, if you have any questions or suggestions, don't hesitate to send me a message. Thank you, and I will meet you soon in our live session.
Okay, thank you, everyone. I see we have some questions here about the tasks that we used in the experiments. So this varied a little between the experiments, but for these initial studies, we focused on the spatial temporal triad. So where, what, and when questions that the participants had to look for among the data. I also see some questions about the overview and getting an overview when you are inside the SDC. So this is something that we want to address now, because the space-time cube is normally not used alone. It's used in combination with other representations, including two-dimensional representations. So one of our next steps, as I mentioned, is integrating those inside the immersive environment and evaluating the best ways to do this. also about getting lost in the data. So this is possible depending on the volume of data, I think, and this is a concern that we have. So we are exploring filtering mechanisms and connected visualizations, as I mentioned, to reduce the volume of visualized trajectories to interact with them individually. Also, someone mentioned something about other more details in another session. So I presented some more details at last year's VIS that some of you probably saw. And also I ask you to contact me and if you need more details, and we can talk about this for the rest of this week. The intention of this presentation was to give you an overview of our work in progress in this immersive space-time cube. Thank you so much.
Thank you very much. That was wonderful. Our next speaker will be Sasha Savelyev.
I started sharing my screen. Okay, hello everybody. My name is Alexander Savelyev. I go by Sasha. Today I want to talk to you about visualization of massive movement data sets with low barrier to entry. I conceptualize this paper as more of a practical talk of interest to practitioners rather than theory-heavy talks, so the low barrier to entry is the emphasis part. So let's go ahead and start. Wonderful. So obviously those of you sitting here know that large movement data sets are commonplace these days, and there's plenty of sources for those. You get your explicit GPS trackings of animate and inanimate entities, and all sorts of other wonderful things such as volunteer geographic data or involuntary geographic data, such as social media that's processed in all clever ways. These types of data sets and big data in general are typically positioned as holding some sort of key to magical betterment of the society and, you know, peoplehood as a whole. Therefore, there's plenty of push in academic and practical literature to explore this data, ideate with it, hypothesize with it, and so forth. Those who actually attempt to explore, ideate, and hypothesize also realize there's a lot of other practical challenges, such as cleaning of that kind of data, organizing it, and if you run any sort of complicated movement analysis models, then calibration of those models and picking the parameters is a big challenge as well. The aspect of one of the sub-challenges that I'm interested to talk about today is the size specifically. So often when the data is large, it's too large to both visualize and comprehend, and that can mean different things. So it can be something as trivial as the data set not fitting in your memory anymore, two problems of overprinting, for example, which a lot of us has already said about, or even more complex things, such as does the visualization you build actually support the task you had in mind? So all of that is hard. You can also think about these kind of challenges as what do the tools present you? So what are the tools available for people who want to make visualizations like this? And I think about it as a spectrum. So on one side of the spectrum, you would have more common solutions, such as ArcPro or Mapbox. They're well-established pieces of software, but they do what they do, and they don't do what they don't do. And visualization of massive movements data sets at the moment is not what they do. On the other side of the spectrum, you get your custom solutions, and there's myriads of papers with fantastic ideas for both computational processing of movement data, automated analytics, geovisual analytics, and whatnot. But in order to implement those techniques in practice, you either have to be the person who invented them or have really deep technical expertise. Then on top of that, of course, you have to be an expert in your domain of interest. And you see the problem. You need to have a really big competent team. Those are hard to put together. My question of interest was, can you do more with less? So do you have to have some sort of atomic nuclear visualization to do a little bit of exploring and thinking, or do you not have to? So the roadmap that I want to present here, kind of a meta template, if you wish, is specifically for very large movement data sets. I'll show you about 80 million records in just a second. The key things are three. First is take your data set and format it as origin, destination, time of arrival, and whatever other things you want to put for each single movement record you got. So it's kind of a giant CSV file with each row being one segment of movement presented. The second thing you need is a kind of a streaming algorithm that would be drawing your data. By streaming, what I mean is it processes records at one at a time, or maybe just a couple. That's another key requirement. And the third one is you have a raster drawing surface, which means you're not drawing complicated objects or keeping anything in memory. You draw pixels, like a tiny little line you draw from one corner to the other. Combine these three elements in a pattern allow you, in essence, to visualize infinite amounts of movement data, not restricted by size at all. Whether the resulting visualization is useful or not, we'll see in just a second. This approach is platform agnostic. I put a little recipe below. If you want to put that together in a web page, that's not a problem. There's many technologies to do that. My case study is implemented in processing because it's popular with non-programmers, and it helps me extend my reach somewhat. So here's a snippet from the video that's uploaded as part of the short paper. I'm going to play it right now. So what you see is Twitter data. If you tweet from one place and then another, I draw a little white line, and all of this is done using the approach I outlined. In this case, what happens is the algorithm reads a bunch of data from the top, and then it draws them as they happen. Right now, you see the overlook of the entire Western Hemisphere coming through, and we're going through the day to night time at a fairly reasonable speed. I'm going to wind back for just a second to highlight an interesting pattern you might or might not have noticed. This is nighttime. This is real-life human data. Take a notice about these flashes you're going to have all of a sudden, parts of the country line up. Those are time zones. You're basically looking at the Americas, in this case, wake up and, immediately report that sort of stuff on Twitter. So that is a broad overview of what could be done with even that simple technique. I also engage in serendipitous discovery. So again, the same sort of visualization, but take a look at where the big yellow arrow is pointing on the screen. You're going to see a little worm starting to emerge in that area, making a tiny trip. And then that worm, in just a few seconds later, is going to make a trip back. So surprisingly, this kind of data set, even though it's not obligatory to tweet every few seconds, some people actually bother to tweet when they drive with sufficient accuracy to have movement data recollected. Here's a couple of fun examples like that. Again, take a look in the corner highlighted with the yellow arrow. Some of those are quite detailed and go on for quite a while. It's essentially a data road trip, if you wish. I hope they were not the person who was tweeting and driving at the same time. Here's one more example of an extremely fine trajectory. You'll notice that most of them are actually kind of disjoint, but the one that just popped up over there and went along, it was fairly high precision in terms of the sampling of the data was fairly intense. And the other thing that I wanted to talk about is, despite the fact that all I'm doing is reading segments of movement one by one and drawing them as little white lines on the screen, you can still throw in a lot of advanced analytical functionality. For example, because they come in one by one, you can filter data live without any computational overhead. Again, here's a snippet from the full video. So here I'm filtering the data to only show movement records above, say, 90 miles an hour. So, whether that's a car or plane, you can think about that. Or, for example, movement seconds that are longer than a certain distance. And all of that is done on the fly without having a supercomputer. It's commodity hardware. Visually wise, this approach is also extremely simplistic. I have an outline for an algorithm later. For example, here I'm changing how quickly I'm washing away the old records by dumping black paint on the screen. And now I'm not washing them away at all. So you can build this kind of overlaid static summaries of the movement if you need a nice screenshot for a presentation somewhere. If you want to, you can speed it up or slow it down. Essentially, it boils down to reading data a little faster or slower. So all of that is still within the realms of that very, very simplistic approach of reading lines one by one and drawing them in a raster surface. So let me pause it up and go to the next screen. So a conclusion, I wanted to wrap up early, and this time maybe I'll save other people a little bit of time for their presentation. So this very, very straightforward approach with minimal programming involved, it does work, and at least it works for 80 million movement records. I don't see any reason why it wouldn't scale for 80 billion movement records. It's also vaguely useful. So the things that you saw in the presentation is you saw spatial temporal pattern, the whole waking up and going to sleep thing. You've seen clusters of proximate activity and further activity. You saw plane-like movement and car-like movement and so forth. We're able to engage in some sort of serendipitous discovery and even contemplate a little bit about what kind of model to use. For example, is your data set really sparse, or is it frequently sampling the actual movement trajectory of the agents you're interested in? And of course, it's best not to oversell. So this, again, was the purpose of this talk, was to show how to do more with less. So can you show infinite amount of movement data with very little technical firepower? And the goal was to show, yes, you can. By no means would I want to claim that this is either the ultimate or even the better kind of approach to solving the problems, at the very least because, and that's the last point, we need more human subject research in this domain. Animation as a tool is generally poorly understood. There's conflicting ideas whether it works or not, and even understanding what kind of tasks for data analysis are better or worse supported by this kind of visualization, that's an outstanding challenge in the room. So I'm happy to answer in Discord when we run out of time, and I'm also happy to take questions if they got them now. I am at 8 minutes and 45 seconds. Thank you so much.
That was fantastic, Sasha. Thank you so much.
You. I'll stop the screen share, right?
Well, thank you so much, Sasha. We really appreciate it. And if you have questions for Sasha, please put them in the Discord or in the YouTube chat. Very much appreciate it.
Thank you. It's wonderful to be here.
Thank you. Okay, so we are moving on to Anita Graser is next. Anita, we'll look forward to seeing your talk.
Thanks. I've started. Good evening from Vienna. My name is Anita Graser, and thank you for this opportunity to share with you some insights of how to explore movement data in notebook environments that I've collected over the last couple of months while working on a Python library for exactly this task. Since my background is in GIS, obviously the first choice that I had for dealing with movement data was to use desktop GIS applications. But if you have ever tried to do that, you probably soon realize that the desktop GIS is not a very good approach for movement data because they mostly build on the simple feature data model, which is either points which don't have any built-in logic about chronological order or about moving object identity, or you have lines which have only a certain set of attributes for the whole trajectory or trajectory segment, and you don't have any information like timestamps or other attribute for each location along these lines. So I had to realize that GIS, while an obvious choice for myself, is probably not the best choice. So I looked around for quite some time, and I ended up with the Pandas data analysis library. And the main reason why Pandas stuck out to me as a suitable way of implementing something for movement data is because it has great support for time series. Since it was developed in a financial modeling context, they obviously had a lot of time series to deal with of prices over time. And they really took care of implementing a lot of useful functionality in that way. And then couple of years ago, we got the addition of GeoPandas. So also the handling of geographic information in these data frames, in this time series, started to take shape. And basically with the time aspect and the spatial time aspect already in place, it seemed like time was ready to do something for movement data as well. And the library that I've been working on over the last couple of months is called Moving Pandas, and it combines exactly those two things. And it brings to the analysts' toolbox a couple of classes that are very useful for dealing with movement data in a very intuitive way. So for individual trajectories or for collections of trajectories, then there are classes which deal with generalizing the trajectory information, with aggregating multiple trajectories into more understandable visualizations, like for flow graphs, for example, for splitting trajectories, for detecting stops, and so on and so forth. But it also covers visualization, and I want to show you a couple of things which I tried over the last couple of months and thought might be interesting to share with you. The basic GeoPandas plotting, which is also used for moving pandas, is static by default. The very basic functionality uses Matplotlib as a backend, and you can plot all kinds of geometries. That works just fine. When you want a background map, you need additional libraries, which are optional. Like here is an example with Contextily, which gives you some background maps, so you have geographic context for your geographic information. If you want an interactive map, you have to look into other solutions, however. And I evaluated two mostly. The one is Folium, which is a library that is built on top of Leaflet. So Leaflet is this web mapping JavaScript library, which is very popular for building web maps in general. And it can certainly be used to visualize geo data frames. So on the left-hand side, you can see one trajectory from the GeoLife dataset visualized. I use a gradient to show directionality because what I'm plotting here is just the sequence of points. The code is kind of involved. It's not very straightforward. And I wasn't too happy with the overall performance of it. Already visualizing this one trajectory wasn't as super smooth as I was hoping it would be. The other library I looked at was HVplot or HoloViews. There's a lot of different names for these related libraries, so that might get a bit confusing. I'm sorry for that. But HoloViews integrates with pandas and with GeoPandas. And basically, instead of the usual pandas and GeoPandas plot function, you just call the HVplot function, and it gives you some really nice interactive graphs. And you can see they are built on bokeh. They have panning, zooming, hovering, pop-ups, everything built in already, and all you need to write is this one line of code, so that's super convenient. Coming back to Moving Pandas builds on GeoPandas, so it uses these two options, the regular Matplotlib plotting as well as the HoloViews HVplot functionality. You can find all the demos that I'm showing here in the GitHub repositories in notebooks that run on MyBinder. I'm still practicing a bit, so one of the links in the paper is incorrect, but here in the presentation I have the correct links. One of the features that I mentioned is stop detection for trajectories. So you can specify the minimum duration for a stop and the diameter of the stop. And depending on the setting, you will obviously get a different amount of stops. And here you can see how this looks like in a notebook environment, how you can easily interact with the resulting stops and discover the details. There's also a way to split the trajectory at all the stops. So in this case, HVplot will automatically assign a different color to each of the segments, which is nice in the plotting. There's also pretty cool integration with another library called Panel, which allows you to create these small interactive applications inside the notebook. So here the sliders and the drop-down widget, they are all just 1 or 2 lines of code, and they can be connected to the functions that draw the map and the chart on the right-hand side. And they automatically update every time I change one of the settings in these user interfaces. So that's another nice thing about the HoloViews libraries, that they bring all these things to the notebooks to make it a more interactive. I also have some flow examples, and that's the one where the link in the paper is wrong. So this has the fixed link on this slide. One thing that you will notice here, there are no arrows here. We had a lot of arrows in previous talks. Unfortunately, these libraries do not support plotting arrows yet. I can only plot lines. I also cannot offset them to the left or the right. So the movement in opposing directions, the 2 lines or the 2 flows are drawn on top of each other because there is no way, no easy way to offset them to either direction, unfortunately, right now. So to wrap this up, HoloViews is great for interactive maps and charts, and they can be linked. It is easy to build small interactive applications. Unfortunately, the cartographic capabilities are rather limited, particularly if you come from a desktop GIS background, you expect something else. And so far as I know, there is no linking and brushing support between maps and charts, unfortunately. On the Moving Pandas side, the target is to have intuitive movement data processing. It covers common analytics tasks like stop detection and generalization. You get support for static and interactive visualizations. So far, the analytical capabilities are quite limited, and it's certainly not suitable for big data like the previous example. But if you want to give it a try, if you have any questions, please reach out, and I'm looking forward to taking questions in Discord. Thank you.
Wonderful. Thank you so much, Anita. We have a question from Natalia Andrienko. Is it possible to draw curved lines with these libraries?
Unfortunately, as far as I know, that's currently not possible, no. I've been opening a couple of feature requests, but I think we would really have to pool some efforts and improve the cartographic capabilities of those underlying libraries. So HoloViews, GeoViews in particular.
Wonderful, that was great. That sounds great. Curved lines are very important. Any other questions for Anita? I'm just checking here in the chat. Okay. Could you please assess the scalability of your implementation?
Yes, as I shortly mentioned in the end, it's not very scalable so far. What I'm mostly waiting for is for GeoPandas to implement multi-core processing. So I know that they are working on that. Currently, everything is on 1 core, and correspondingly, it's very, very slow. On the HoloVis side, there are some attempts to speed up rendering, which currently are mostly working for point datasets. So there's some super fast implementation which runs on the graphic cards for making basically density maps, heat maps of points. As far as I've experienced, those unfortunately don't work for lines yet. So there are no line densities or anything similar. But we are getting there. All of these things are very much in flux and under development right now.
Great, that sounds wonderful. We'll ask one more very quick question, and then I would refer to you to Discord to answer any more questions for Anita. What are the limitations for these libraries? I can't think that will be a short answer, but I know you'll do your best.
Yeah, that's a question. We already discussed the dataset size, which is a limitation right now. Installation-wise, it as far as I know, works on all operating systems. It's a bit hard to install on Windows, but it's possible. I recommend to install via Conda. And as I mentioned, all the examples, they run online in MyBinder notebooks. So even if you cannot get it installed right now, you can try them out. So that's probably the short version.
That's great. Thank you so much, Anita. That was wonderful.
Thank you.
Round of applause there. And for our last talk, for the short paper session, we have Arnab Chakrabarty.
Hi everyone. So today I'm going to present my paper, which is titled as a visualization system for high dimensional data stream using complex event processing. Yeah, so as the name is quite big, let me go through each of the terms and explain what it means. So as a motivation to this, just a moment. Okay, so as a motivation to it, I would like to draw your attention first to what does high dimensional data stream mean. So currently it is an open challenge because most of the data today is now high dimensional, and visualizing high dimensional data is definitely one of the challenges where the research community is very much interested and is working quite well. So one of the basic needs is we need to have at this hour is to have fast and responsive visualizations, because the data is growing and it's quite fast. And as an example, I would like to direct to the main ideology of this workshop, which is geospatial data visualization, which again deals with massive data sets, as we have heard from the previous talks. And why do we need to visualize it? Because we need to identify the hidden patterns and trends, and that kind of promotes the data-driven decisions that we need to make at the end of the day. So the idea that we present in this paper is basically the application of feature selection and dimensional reduction for data visualizations. So as I said, the current systems are which deals with high dimensional data streams for visualizing visualizations are slow, they're unresponsive. Sometimes when the data size grows and there is always a problem of data overlapping due to this high stream of data, velocity of data. And yes, the famous word like the curse of dimensionality always exists, because when we try to visualize a large amount of data in a small screen, then there is always a visual clutter, and obviously there is a limitation of human cognitive ability, because we cannot perceive more than 3 dimensions. I mean, it can, okay, can be colors and shapes, but if there are other dimensions that are all rendered to the screen, sometimes it becomes difficult for us, for the human eyes to perceive. And on a technical perspective, definitely there is memory and CPU overheads. Okay, we can use better systems, we can spend money to buy fancy hardwares, but at the end of the day, that does not somehow overcome the previous point of human cognition. So the idea is, okay, this is, sorry, so this is bad because I wanted to share another screen. Okay. So the idea is to how to use data reduction. Yeah. So one of the important solution is feature extraction, but there in that we kind of combine different features in a data set and try to build a new feature. So this results in an information loss. And also it's not good for analytics, because sometimes this combination of different features and doesn't result in the better understanding of the data, because you get a new feature which is somehow somebody who is not aware what the data is doing, he may not understand it. So another way is to have feature selection. Yeah, so that is somehow to filter the data that we need, but they have also some limitations. For example, having large volumes of streams, and also the memory and the CPU limitations. So our solution is to use feature selection using complex event processing. So what is complex event processing? So they are used for processing dynamic streams with no prior knowledge, and the method is used for analyzing large volumes of data streams. And yeah, there are some systems which can be plunked upon the complex which can the CEP engine, and for example the big data processing engines like Kafka and Spark. So basically in our approach, we this is what we do is that we try to present Storm Esper is a CEP engine. So it's we distributed topology we try to present, and we present it in a much technical details, which can be seen in the paper. Here, due to lack of time, I'm not going to explain in details, but you are free to contact me or ask offline some questions. So basically the idea is this. So let's assume we have a high dimensional weather data, and there we have different weather attributes like temperature, pressure, humidity, and lots of other attributes which are not actually needed for our analysis. Yeah. So what we need to do, we need to first identify which of the features are actually of interest to us. And in this case, we assume that the features which are changing with time, and these are the features that are actually used for trend detection. And this way, we are using the CEP engine for feature selection, because in the CEP engine, we can actually write our custom queries. For example, we can create an event here, for example, a weather event. And let's say in the step 2, we can say, okay, which are the features which are changing with time? And we can also set a time window, let's say for 5 seconds, and then extract only those features which are returned by the execution of this query. And then we can run another query which can detect trends, for example, an increasing trend or a decreasing trend, such like that. So for example, here we have a visualization dashboard, and in this dashboard, which we also present as like the outcome of this our architecture, which we kind of get the real data to visualize, is that we connect it to a streaming any streaming API. We get the data, we run the we actually build the query in the CEP engine, and then in this dashboard we can see that the features which are in this, let's say, data set with 1,000 dimensions or more, and only those features which the user has actually set in the query, those gets filtered out and those gets actually visualized. And simultaneously we can also see what are the different trends that getting generated. So is let's say feature 1, for example, here it's temperature, so it has a decreasing trend. For example, again after some time, it's the temperature, wind direction, and wet temperature that has an increasing trend, and these trends are also getting detected. So what are the takeaways? So the takeaways from our research is also a start of the work or the idea which is presented in the paper, but there is also a possibility to further develop it. So and to summarize it, that we can I can tell that this is the first idea where we implemented this complex event processing on top of a streaming platform for feature selection and trend detection for high dimensional data streams. Yes, it's a generic system and can be developed using this Esper CEP that can intake any streaming data source. And the main important thing is that we don't have any prior knowledge of the feature. So it is kind of doing an unsupervised feature selection. So we don't know what feature, what are the features are before, or what are the pointers to the data set. Yeah? And that is very efficient in doing this feature selection. And since this Esper storm topology can be deployed in real-time environment, so we can see this it can handle a large set data set in a real-time environment, and it's more responsive and faster, and the trends or evolution of the data can be identified. Yes, so we can set any data plots which we like, and we can see that the different trends are getting easily detected. So the details of the implementation is set in the paper, and you can also see the documentation which has a link which has the detailed explanation how the features are developed, how we actually the technicalities of the storm and Esper, inducing the Esper topology on top of the storm and how we developed it. It's like a technical report, and you can find it. But again, if you have any questions, please feel free to ask. Even you can write me some email and ask about it. And yes, I still have, I guess, 10 seconds. So sorry if I was a bit fast. So thank you for your time.
Wonderful. Thank you so much, Arnab. Can we take any questions that may be in the chat for you? I haven't seen any just yet, but people may pop up with something. We have claps, a lot of claps. Okay, great. Well, I'm sure that some people are going to be very interested in your dashboard and its functionalities and some of your future plans for it. So you may get some nice questions from Discord, from the YouTube chat as we move on. And we would just like to thank you very much.
Thank you.
Great. All right, everybody, that concludes the first part of our program on the short papers. We had 5 wonderful short papers and a really great keynote from Jeremy White. Now we're going to have social time. I've included the link, the Remo link, in a bunch of different places. It's located almost everywhere. And hopefully you can log in and chat with some of the speakers and some of the organizers and with each other. I will note that you do need to register for this, but it's free and we think that it's worth it. One last thing is that we'll be restarting here around 4:10 my time, 2:10 local conference time to continue. Thank you.
Program developers spend significant time on optimizing and tuning applications. But working with binary code to understand what compiler optimizations were applied can be challenging. We present our visual analytics system, CCNAP, designed to identify and assess compiler optimizations in binary code. Check out our paper to learn more.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Suppose you want to see the overall commit structure of a new project repository. Using Git client tools, Git some network, or Git log command is quite burdensome to get overview and navigate data. We presented Gitru as an interactive visual analytics system for the Git metadata to help users explore and understand the context of development history.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained path extraction method, a river-based visualization, and a contribution analysis method.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
We present TransVis, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIV matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user-selected path to justify and reason the AD analysis.
Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
CarxS is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons, and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and exposed through our Morse-Mel complex guided semi-automatic tracing tool. The topological ridge graph underlying our MSC guided tool is robust against gaps in the signal.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heat map view shows the stability of the selected region and provides region adjustment by directly clicking.
Reservis is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
We demonstrate that people can use the spatial cues available in virtual reality to help them effectively remember and recall scholarly articles. We used a virtual coffee shop and asked participants to remember 4 abstracts from scientific publications, and we termed this method a virtual reality memory palace variant.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
The success of convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the thinking model is not easy to understand. We introduced the Explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural network. Using the Explainer, users can progressively explore the thinking model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed a data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
We present StratGraphics, an approach for designing data-agnostic and fully reusable visualization templates. StratGraphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
If machine learning were like education, we would like to test what concepts our student, the model, has learned. Has it learned the concept of object rotation? Does additional text help with object recognition? We need a methodology and platform for conducting such tests. In this paper, we present a novel visual analytics tool that enables hypothesis-based evaluation of machine learned models.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
Attention mechanisms have greatly improved the performance of many language models, yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
As data is changing, our understanding of data should be updated correspondingly. Based on machine learning approaches, we formulate a drift-level index to monitor the evolution of multi-source data, which allows users to capture and reason significant changes from time series data. The proposed visual analytics system is called Concept Explorer. More details can be found in our talk.
Linking and brushing is very useful for interactive visual data exploration. Data-driven brushing tools are getting popular recently and achieve good results, for example the Mahanoda-based brush and the CN-based brush. However, these brushing tools are optimized by the data from a large number of users, which are not suitable for everyone. In this paper, we introduce an adaptive brush model which takes the user in a loop to improve the brushing accuracy.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph models.
Hello, everybody. Welcome back. I'm Somayeh, Assistant Professor of Spatial Data Science at UC Santa Barbara. I would like to welcome you to the second session of our MoVIS workshop. First, I'd like to thank Alan and Clio for all the work they did. I'm so impressed by Clio's ability to navigate all these different technologies. Thank you for that. And thanks for having me on board. I also like to thank all presenters of the previous session and our keynote speaker. And now we have 4 work in progress demos that I'm very excited about to see soon. Our first speaker is Jugal Patel. Thanks for your presentation. Please take it away.
Hi everyone. So the work in progress that we're trying to present is a sort of adaptive framework for simulating movement trajectories, which I like to refer to as transferring decision boundaries onto a geographic space. But what we really have done is just extracted rules for agent-based modeling from movement data, and we use classification trees to do that. And so explicitly, the decision boundaries that are referred to are the partitions in classification trees, and the geographic space is the place that a troop of the olive baboons calls home in Impala, Kenya. So just a quick background is just that there's this troop in Impala that have been monitored, and this was a very a pretty famous data set now, and it was the first time most of a social group was monitored for every second between their daily range period. And it's become a sort of a landmark study to say that decision-making when in movement is locally determined, and it's not determined just by alpha members, at least in a primate group. So in terms of the framework, we're going from a sort of observed movement data to a sort of a simulation of that data. So of course we start with a data source. So that will be the paper that I just mentioned earlier, where the animation was from, but also MoveBank, where that data is stored. And so the next sort of obvious step that comes is cleaning and pre-processing that data. And I'll try to zip through this and so I relied heavily on the tidyverse and R to do this. And keeping in mind that we wanted to perform path segmentation to our trajectories, we used aid habitat as our packet as a R package to derive velocity from the points, and we applied a simple threshold based on the error that was reported with the GPS loggers instead of some sort of ecological insight. So what we did was we took the error, which was 1.3 meters for each logged position, and we said that any movement that's happening greater than that, so any velocity that's recorded greater than that would be an indication of movement type behaviors. So it's sort of like associations with a behavior type instead of like an ecological understanding of animal behavior. And so it's important to note, like we're trying to associate with something, and the associations are environmental features in the scene. So here on the left, I'm just showing a Euclidean distance raster to tree features in green here. And then on the right, I have in yellow trails. But we also collected rivers and clearing sites. So with these sort of associations, we were ready for classification trees to get involved. So we went to Python and we turned specifically to scikit-learn because they have very popular documentation for classification trees. And so from these classification trees, we want to get explicit rules that we can inform agents' behavior on. So here I've just sort of listed on a scroll agent rules with features and a certain value. But I would say that these are the rules that will inform a common surface instead of the actual agents. And I'll get into that in a sec, but just to say that we made these simulations using NetLoco. It's also very popular. Okay, so cleaning, pre-processing, very simple stuff that we did to start with was just missing data and correcting for inconsistent time lags. I've already told you about the path segmentation, and I'll just sort of walk you through what we did, which is start with full data set. We split that up into a validation. We set aside data for validation, which was days 3, 6, 9, and 11 for where the troop had gone. For the rest of the data, we split it up into a training data set and a validation data set, which was 80 and 20% split. Yeah, so into the more interesting bits. So when we're actually dealing with the classification tree, we're making partitions in our data set based on some sort of rule that we've come up with. So we used Gini impurity as that sort of optimization criteria. And this is the data, this is the output from that classification tree. And so broadly, where it goes blue, we're saying that there is evidence for the points in that subset of data to belong to moving characteristics. And then for the oranges, we're sort of saying that there isn't data. So it's sort of accepting null for the orange ones and rejecting null and accepting the alternate for the blue boxes. So we're just going to zoom in and see 3 of these nodes. So node 3 has to do with the trail feature, some meters away, 76 meters away, it says, as well as what's important is the Gini impurity value. So Gini impurity can sort of be understood as an inverse of the certainty that's expressed locally in this rule. And I think, like, without getting too into the nitty-gritty, like, these are the 2 key pieces of information that are being expressed at each node. So each of these nodes can come up with sort of a local decision boundary. And so the first 2 here both have to do with trails, but you can see that there was different values associated with them. So there's different outputs. And then as well as the one on the node 5, there was a tree. So these are all the trees and sort of that distance raster as well. And what's the interesting bit here is how we can sort of combine these outputs and have a common surface that includes all of these local rules to sort of make a more global understanding of what's happening. So that was just 3 rules. And what you'd want to do is you'd want to take the entire decision tree shown here in the middle to make a global surface, which is here that we have on the left. And so you can see that there are certain areas where there's lots of probability that the troops are involving in movement behavior. So it's with the trails is one of the key criteria along rivers. But I would want to say that there's also an expression of uncertainty happening by the classification tree. And that's explicitly the orange sort of boxes that were happening. So these are, importantly, that this is a binary classification problem and not a multi-class classification problem. So these aren't really saying that there's another behavior type. It's just saying that it's not movement behavior type. So taken together, we take these 2 surfaces and they've sort of been, so the movement surface itself is what the agents will run on. And I've listed the sort of programmatic agent rules that were expressed in our model as well on the left there. But since I have 30 seconds, I'll go right to the model output. And you can see here the blue lines are where the trajectories of the actual observed baboons were, while the white sort of areas are where the simulations, the paths that the simulations took and sort of the cells that they visited. So I'll keep this up in the next slide as well, on the right here. And on the left here is our sort of our initial validation effort. So as I had said earlier, days 3, 6, and 11 and 9 were our validation data set. So here, what you want to look for are the green areas where we're saying the model is both close to the actual observed trajectories, as well as expressing high frequency at which it's visited those specific cells. And then green and blue are sort of cases where one of those is true and one of them isn't true. And sort of to wrap up, very open to feedback. Thank you, and yeah.
Well, thank you so much. We have some questions in the chat. There's a question about, could you please assess the scalability of your implementation?
Scalability in terms of like trying to make simulations for other regions or other animals, it's probably not very scalable unless you're getting data for these new areas as well. But in terms of scaling, in terms of like generalizability, just in classification tree understanding, like there's ensemble methods that would be very interesting. There's also, yeah, the ensemble methods would probably be the most interesting way to sort of scale something like this. I think that answers maybe.
Yeah, and you mentioned that you are using different platforms, like you are using R, Python, NetLogo, and multiple different tools. Could you talk a little about how you integrate all these and how the connection between all this works in your work, and whether you find it feasible to switch between platforms, and what the benefit of using multiple platforms is?
I think like just the last bit, like the benefits to different platforms is that these platforms have different key advantages or disadvantages. So just like that's just like a basic answer for that last bit. But for the first part, like actually integrating all of the different platforms, it can be tricky. But R and Python are there's very common frameworks to go back and forth between the two. And for NetLogo, I think there's a package that lets you program in our NetLogo models. We didn't do that. We actually had different people work on different parts, and we were sort of interfacing in an old school way, or through Slack, I guess, which is old school now. But that was our integration process.
Thank you so much. Let me check if there's any question. Okay, so I would move on to the next speaker to save time. So we have Shenxiao Gao, our next speaker. Please take it away. Thank you.
Okay, hello everyone. My name is Chen Xiaoguo. I go by Atlas. So I am a PhD student at University of Wisconsin Madison. Today I will be presenting my recent research about framing Twitter trajectory visualization, a comparison between hurricane evacuation and pandemic lockdown. So this is just a work in progress. So first I'll introduce the background as well as the objectivity. And then I will talk about my framework about trajectory visualization, including these parts. And then I will summarize some characteristics of social media data trajectories. And then I will quickly go through some case studies I've done before. One I'm still exploring, the hurricane evacuation as well as the pandemic lockdown. So first, as the disaster events increasing, the human mobility draws our broad attentions in playing key roles in disaster mitigation response, such as getting evacuated or quarantined or locked down. So location-based social media has already been widely used as a social sense approach. Besides the individual locations as point data, the trajectories also have great potentials in exploring the movement patterns. While they are still not yet being examined comprehensively and systematically. And one of the reasons is that there's limitations existing in social media data, make this kind of data set huge, but also sparse. So my objective here is to first summarize the general forms for trajectory-based realizations, and then have a quick discussion on advantages and disadvantages of social media trajectories, and also go through some case studies to reflect those realization forms as well as the characteristics of social media. So first, in terms of the trajectory realization framework, I will define the trajectory as well as some basic visual primitives quickly, and then go through the 3 dimensions of what I did in this framework. So first, trajectory here means if there's the same object and they move to a different place, well, typically at different point, and definitely there will be 2 different time points. So their attribute, either qualitative or quantitative, could be either same or different. So by nature, there could be a distance, and as well as the direction is regarding the space, and also the duration, or as well as the speed for the temporal information. Also, there could be change or average level of the attribute information. And for the visual primitives here, you can see there's a 3x4 charts showing how the point data, line data, polygon data, as well as cell data could be integrated with our trajectories, which means like origin destination or origin destination pairs. So the cell kind of data here means not only the squares, but could also be circle, hexagon, or other types. So these visual primitives work as the dimension 1. And for dimension 2, we will go through some analytical levels of our realization forms. So first is the raw data or enumerated units. And second would be adjusted level, which will have the same account as the raw data, but there are some modifications. The third level will be aggregated level. There will be less count, but maybe in other forms or shapes or styles. And the fourth level would be density-based, then cluster-based, hotspot-based, from a basic level to a more advanced level of analysis. So here is a complete form of what I'm going to summarize here. You can say point, line, polygon, cells. Another dimension is from raw level to the hotspot level. Actually, I feel this form of every cells of this table, but due to the time limitation, I don't have time to explain them one by one. So let me take a quick example of the line form, which would be probably the most complicated one. So you can see after the basic level, the raw level, there will be adjusted level, which means we can relocate the trajectories by either origin or destinations, or we can make those symbols be proportional to our original level. And we can also apply both, be relocated and also proportional. And for the aggregated level, it's also pretty easy to understand. It's basically kind of network. So due to the time limitation, I will not go through this, but it's very similar for the other forms of spatial primitives, visual primitives. And in terms of time, I hear both the idea from many resources. So basically, we can categorize those representation of time in trajectory visualization in terms of static or dynamic, or single form or multiple forms, and then interactive or non-interactive, as well as how the time is represented either in visuals, visual variables, or in multiple forms, or also work as time itself, which means animation or something like that. And the third, I will also very quickly go through those non-cartographic representation of the trajectories. But they all have some sort of representation of spatial information. So here we can say there are some forms of the visualizations of the non-cartographic representation. And I summarize some of the characteristics of them, but let's skip to the next part. So for the social media trajectories, definitely there are quite a lot of advantages, like huge volume, low cost, instant, great connectivity, or rich forms. But my focus today is on the disadvantages. I will categorize them into time, space, and content. So issues with time, during disasters, specifically, there are not a lot of resources to use the social media platform. So there are accessibility issue. And also the distribution in time is also pretty sparse, which lead to an overall incomplete picture. So which will bring big difficulties in how to draw the entire events comprehensively. And also it's difficult to associate the time to a 2-point trajectory. We will talk about this later. So in terms of space, different regions have different availability of social media data. And also there are uneven distribution among different type of regions. And also the precise locations are kind of limited, especially Twitter has removed this function since 2017, 19. And the location can sometimes be arbitrarily selected by the user, which brings another issue for us. And also multiple geographic scales will bring another kind of troubles for analysis and realization. Issue with content, the users are not correctly represent the real population. It's highly biased, maybe by gender, age, and something other. And also it's dominated by a small proportion of users. There are always a group of active users which post the majority of the social media content. And also the quality is kind of low in general. There are also broad discussion of the privacy issues. So we will try our best to avoid the individual level of any kind. So quickly go through the two case studies. The first one is the 2017 Hurricane Harvey. I will mostly focus on Hurricane Harvey in this presentation. So this is the overall picture of about 150,000 trajectories. It's not the number of tweets, it's the number of trajectories. So for example, I introduced this kind of adjusted level of line representation. We can regard those trajectories as the lines. Then we move them to a new location, but change the size proportionally. So we can get such kind of representation of origins. So in here in these examples, this kind of symbol will show the change of directions among different stages of the disasters. And the aggregated level is actually easier to understand. It's like the social network with different connections of magnitude. And polygon level is also easier to understand. For example, we can compare the level of the in and out. And some examples of the non-cartographic representation, we can, well, definitely regarding space somehow. Like we can summarize the inbound, outbound as a representation of spatial information, and also these windrows charts will show the movement directions, also kind of space. So in the second case study, so this year's coronavirus, I collected like from Twitter 5 million trajectories from March to August. And here I will probably mostly introduce the issues I mentioned before. If we do not specify the scale, the geographic scale of our data, we will meet this kind of weird errors, like the Florida level of data will be moved or located at the centroid of Florida, which totally doesn't make sense. And also, if we plot the user, the number of users by their cumulative number of the trajectory, we will see about half of the users contributes to 80% of all the trajectories. And you can see even 3/4 of them has less than like 3 trajectories overall. And also in terms of how to define the time of trajectories, we have multiple options, like either use the time of origins or time of destinations or time in the middle. Or another alternative way is to average the time for the points that are origins and the destinations. So here I quickly plot the Twitter-based moving distance compared with the daily increase of the
Alice, we're going to give you one more minute here. Please wrap up. Thank you.
Yes. And so we can see there are 2 decreases of the moving distance, which happened right after the 2 major pandemic peaks, but we can see the delay in the time. So definitely there are a lot of things to be explored, and I will quickly summary instead of make the conclusion here of today's presentation. I generate a framework of the trajectory realization and focus on the characteristics of the social media data, then quickly look through some examples in my case studies. Okay, in the future, we can explore more in the cartographic realization as well as generate more direct comparison between those case events. Okay, thank you.
Thank you so much. There's one question about the third dimension, whether you find it necessary for interactive visualization of these plots or not.
The third dimensions, I think you mean this non-cartographic representation. So these are just the general summary of those representation forms that could include the spatial information and which will be which are used actually widely in trajectory realization, but not specifically related to our trajectories. So these are just the possibilities.
Okay, thank you. Our next speaker is Hanan Salman.
Okay, good afternoon. I'm speaking today on behalf of my co-authors, Yunhang Hang, John Kastner, and Hong Wei. And what we're trying to do is visualize spatiotemporal varying COVID-19 data. And okay, now yeah, existing systems. And what I'm trying to do is my mouse is not moving. Just a second. Yeah, I'm just not getting my mouse to work.
That's okay though. We see your slides if you could continue.
Okay, no, I'm trying even to make it. Okay. All right, so the existing systems are mostly mashups, and when they try to look at spatial data, and the point I'm trying to make is that when you zoom in, you don't get more data. And here is an example from the Washington Post or New York Times of looking at animated or data that's time varying. So these are rates of, I think public per capita cases of COVID-19. And so that usually you have one graph per region or location. And what we do is have more continuous modeling of the animation. So if you look at this picture here, they're just separate graphs. The fact that, that let's say California is next to Arizona or Nevada is not reflected here. So if one of them changes, the change is, you can't tell if it easily, if that change also propagates to a spatially proximate neighboring state and things like that. So also, if you look at these type of plots, you're always plotting the time on the bottom, and then you can you can say, well, I can plot lots of variables here, but really you can't really do more than two variables in the sense that you utilize the y-axis, namely the left y-axis and the right y-axis, to give the scale of two different parameters. So that's really our goal, is to get over this type of problem, and also the business about the zoom. Okay, so and what the other point I'm going to make is that we're using data from Johns Hopkins just like everybody else does. Okay, so you see, I'm being hidden. Okay, anyway, I do it without seeing all my screen because my mouse just won't work. All right. Anyway, so the types of queries we have on spatial data are really location-based or feature-based. Where location-based is given a location or a time, you would like to know what are the values of different variables or rates. Location queries are based on, given a location, what's there. Okay. Now, here is the example of our user interface. And this is an example giving you the incidence and mortality rates for South America for 2020. What you'd really be seeing is you'd see them moving, changing from day to day. Now, here we have sort of in our control panel the ability to control both the animation, the location, and the view. And we have one panel with help information. Now, here is an example query, which basically shows you what we're doing. And what we're going to do is set our animation focus to the US. What that means is that we'll be plotting the data for US as things move all the time, as the time changes. And we're going to use a 30-day animation window. Okay, one of the things you can do with the system is it runs in two modes. One is called total mode, which gives you the total number of recoveries, deaths, confirmed cases, something like that over a time period. Another mode is what we call window mode. Window mode allows you to look at any number of days, consecutive days, and have them animate as you're moving along over time. And so that, as you're moving along over time, it could be a daily rate, or you could be plotting a cumulative rate. So how much, that's like when they say they'll reopen if they have so many, less than 300 confirmed cases over a week or 2 weeks, whatever. So here in our example, we have an animation range from February through December, and we want to see the mortality and incidence rates. So what are we doing here? Let's give it a go. And this is, I hope I can get this. Oh, it's working. Okay, so this is a video. Okay, so what we'll see now is a progression from February. So you see, New York is heavy here, okay? You see here in New York, and as time goes on, it gets bigger and bigger. You can see and then it gets smaller, but look what happens. The disease is progressing to the south. So remember in Florida, it gets bigger and bigger, and here's Texas, and this is like July. And then in September or so, you see it's getting bigger and bigger in the Northwest. So this is the basic thing that's going on here, and namely that you have this variation, and we use what we call geocircles to show you with the value. So how many deaths, or how many, not how many, but in this case it was a mortality rate, but it could also be death, and the incidence rate, or then just number of confirmed cases. But they're drawn on the map with these circles, and the radii or the circles are the values. So basically the animation shows you the circles changing over time. And that's what I said before, when you have two circles next to each other, that means they're spatially proximate. So you have a very a nice way of looking at spatial variability. We also have a nice way of looking at temporal variability by what we call time sliders. And that's really if you saw on the demo, you saw that there was a line at the bottom of the map with a date for each one. So you could just slide that and see what the values are just over time. Okay, so here is the radius scale, and you can the radius is really the value, but there are a lot of different scaling. Okay, so here, okay, just another example of them. So the idea is that you want to change them so that if they're small, you may want to make them bigger. And here you could see that the next thing we'll do. Okay, this is really important, because when you draw the thing, okay, no. Okay, hopefully we'll get to the next slide. Okay, so we talked about scaling. Scaling was really important because a lot of times you have very small values, small numbers. And when you have the small numbers, you got to draw the circles. Well, they all merge, okay? And you can't really differentiate between them. So the scaling is a nice way to enlarge the scale so that you get away from things being too small. Okay, now normalization is another thing. So we have both the absolute data, and normalized data would be what I would do, like number of incidents or confirmed cases per 100,000, which is what seems to be the conventional use of this statistic. So here is an example of this, and let me just start it. See, I guess this should work. Okay. So what you can see, Okay, so that's this one. And I have to find where my mouse is. Okay. Okay, all right. And this is, what was this? What's the title of this? This one that we saw already. See, I can't see it because my mouse is not working.
And could you please wrap up in 1 minute? We have to
Yeah,
move on to
sure.
the next
Okay.
speaker. Thank you, Hannah.
All right, sorry about this. Anyway, let's look at this one here. Okay, this one is called Sweden and Herd Mentality. And what we'll show you is the difference between Sweden, let's say Israel and its neighbors. And you can see here the difference in the mortality rates. Namely, Sweden has 5.99% mortality versus 0.68 in Israel. They're about the same population. And the incidence rate, however, in Israel was four times as much as in Sweden. So this pretty much conveys, I can't believe this. Do you see? Oh, there. We're there. Okay, this is 50 seconds. Okay, and what you'll see here now is looking at Sweden. Okay, so now you see over the time, this is the time slider on the bottom here. Okay, and what happens, you see Sweden in red and black here. These are the neighboring countries, and it's a big difference between Sweden and the neighboring countries. The deaths are much higher. Here we looked at in Israel and Sweden, and you can just the data summaries, and you can see again that the death rate was really high there. Okay. All right, and this is an example of hot spots when Italy and Spain and France were hot in March, and you can see they're much bigger than their other countries nearby. Careful if you use logarithmic scales. If you use base 10, it's almost useless because it masks the differences, whereas natural logs work better. And you can run this system after I go home and figure out what was, it ran, but I had a lot of troubles today. The big thing we need is more data. We'd like to do positivity, but there's not that much positivity data, or it's not very complete. The system right now is complete for Italy, and US has very good data for that. All right, sorry to all these.
Thank you so much. Yes, we have to move on to the next speaker. Unfortunately, we don't have much time. Our next, please help me thank Hanan for his presentation. Thank you. Our next speaker is Xiao Fan Lian.
Do I need to wait for countdown, or is it starting now?
That's a great question.
I don't know that. Are we starting?
Hello, everyone. Good afternoon. My name is Xiaofan Liang. I'm here to present the work with my advisor, Dr. Clio Andris, on a tutorial for visualizing non-planar networks. So the goal of our tutorial is to visualize and analyze non-planar data. So as an example, you can see graphs on the right where origin and destinations of a flight network are targets, while planar networks such as subways lines would not be a target for our tutorial. The audience of our tutorials are researchers and practitioners with basic knowledge of R, especially with some knowledge of tidyverse packages, such as GIS analysts who want to display social networks and origin destination data, or social network analysts who want to use geographic analysis. Our work built on existing GIS concepts and methods and existing network science concepts and methods. We also leveraged the user studies and information visualization principles insights. So why this tutorial? First of all, it's convenient. Traditional GIS software is difficult to work with network relationships and cannot store data as graph structures. Traditional network visualization software, such as GAFI or D3, cannot conduct spatial analysis. In addition, our code can be replicated easily, and we have abundant amount of existing packages that we can build on. Secondly, it's educational. So we provide sample data sets, detailed comments on code, replicable examples, and state-of-the-art visualizations for beginners to follow. And we also give step-by-step instructions. Our current choice of packages, including TMAP, SF, iGraph, and a few other ones. TMAP is mainly for creating static and interactive maps. SF is for running spatial operations on geometry. iGraph is a standard package in R to conduct network analysis on data. We also know that there are a few alternatives out there, including ggplot2, cartography, and OD. So in our comparison, we think that so for the comparison, the powerful dimensions is about how well they can visualize OD data. The interactive dimension measures whether they allow interactive features. The flexibility refers to whether they can build onto other softwares and whether they allow customizations. And the intuitive dimension is really about, it's kind of subjective. It's more value based on how much is intuitive for people who already know GIS. So in this kind of measurement, we think TMAP is a good option, even though it's still lacking in some function to map spatial social networks, but it's very interactive, it's flexible, and in particular, the way the code or layer are very similar to GIS software. So we'll demonstrate later with some examples to show what that looks like. The data sets in our tutorials are meant to demonstrate mapping challenges, such as overlaps of node and edges. So we have two main data sets. So one data set is a spatial network data set, including distribution of mafia members in US collected by Dan Della Posta. The second data set is the Lotus work home commutes data from US Census that is publicly available for download. In addition, our code also includes automatic download of sample data sets from Friendly Cities Lab GitHub. So in terms of the contents, so our tutorial have 4 main sections right now. So the first main section is concerned about network matrix. So we teaches people what is the basic network graph data formats, what are the network matrices, such as degree centrality, and how to do some aspatial iGraph visualizations. The second section is concerned with visualizing nodes. So how to convert coordinate to points, how to visualize nodes by color and size. Visualizing edges will concern about converting points to lines, visualizing edges by color and size, edge direction, and edge arc. And we are also exploring advanced topics such as network modularities, edge bundling in R, interactive maps, and isochrones. In terms of progress, we have pretty much completed the first 2. Still working on visualizing edges, mostly because the edge direction, edge arc are not supported by TMAP right now, though we had communicated with the software developer and they are looking for some solution to implement it. And we have barely started to work on the advanced topics. So here I want to exit the presentation and switch gear to show what the tutorial looks like. Hopefully this shows the interface of the tutorial. If not, please let me know. So this is what the interface looked like. We implemented using bookdown, a package in R, which generate a minimal book examples, where you can have an interface with chapters. You can click around and reference different things. And we have code chunks interchanged with text that helps explain. And examples, chapters like this, we will brief about the main contents of the chapter and show how the graph could evolve from the simplest code examples to the most complicated one, including visualizing edges, which is similar, where we show the bare bone examples and how it evolved to a more complicated examples. So back to the presentation. So there are a lot of aesthetic considerations and visual variable encodings that we have not implemented yet for this tutorial. And this is definitely the future work that we need to focus on. So these graphs illustrated some of the complexity in visualizing flow data, including origin and destination, the attributes of flows, and the geometry and their arrangements. In addition to the aesthetics consideration mentioned earlier, we also have the view outlines here. And also we are going to follow the principle of net-vis nirvana, which is how we define what a good visualization will be like for this kind of graph, such as every node is visible. Every node you can count the edges, every link you can follow it from source to destinations, and the clusters and outliers are identifiable. It is an ideal situation, but this is the goal that we are trying to reach for our visualizations. The next step, so we will continue to work on advanced non-planar networks topics and visualizations. We will also integrate more information on spatial joins and spatial statistics for audience that are not familiar with the GIS. And we really, really welcome collaborations and feedback on our tutorials. And I also want to make an acknowledgement to Georgia Tech Institute for Data Engineering and Science for providing a scholarship for me to work on this project. And if you have any questions, you can contact me by my email or follow our lab's Twitter, Friendly Cities, to see when the tutorial will be launched, hopefully in spring 2021. Thank you very much.
Thank you so much. Would this be available for others to look at and comment on, and how can we access that?
This is a great question. So I'm running into a little bit of error of publishing it online right now. So it's not available online at the moment. So if you have a strong interest in collaborating and contributing code or work together on this project, please contact me. But now it's not yet fully available online yet.
Thank you so much. Please join me to thank our speaker. So I need to share my screen now. Can I share my screen now?
Yes, I am exiting the presentation and now I finally find the stop share button.
Okay. thanks everybody again. Please join me to thank all our presenters. Here, I would like to take a few moments to highlight the importance of bringing data analytics and visualization together with, for a human-centered movement data science. As we saw today, we saw different types of data set that are available and are being shared widely with our community. So we have data of discrete trajectories, and we have aggregate flow data that is commonly shared on different platforms using different companies, and different views of movement, such as following movement trajectories and basically observing movements from a set of fixed locations. So this is a great opportunity for our community to explore this data and develop tools to study movement. As we all know and work with movement data are very complex and incorporate multiple dimensions, including space, time, and context. Context would be like in the circumstances and the condition of movement, like the environment within which movement happens. And we need to bring all this together for a better visualization and informative visualization to inform an analysis and develop hypotheses. As an example of visualization, I use this classic albatrosses example all the time. Here you can see the visualization of several albatrosses going from Galapagos Island to the Peruvian coast. So they do these foraging flights regularly, and they forage along the Peruvian coast and go back to their nests to feed their chick. The red thin lines here shows albatrosses strains to headwind, and then the blue thick line shows the faster flight back to Galapagos. Informative visualizations can help us to develop hypotheses about, for example, here, how wind supports this movement of albatrosses, and how they are assisted by wind, or they follow their intuition to find food. And these visualizations are very important for us to develop new hypotheses, to explore our data, and inform our analysis. So the aim of computational movement research is to understand and predict movement. At the heart, we have movement visualization, and we developed data-driven analytics to explore movement data and learn insight about behavior of individuals and movement flows, and use that to inform our theory-driven models and techniques to model and predict movement. Here, it is important to have collaboration with domain science. As you know, that movement applies to many fields. Transportation is one domain, and movement ecology is the other domain that can help us inform our methods and visualization techniques. And visualization plays a great, very significant role here to integrate data-driven analysis and human knowledge to enhance our data science. It can help us explore raw data sets, formulate hypotheses, and reveal hidden patterns. It can help us to monitor the work processes of our algorithms, and also help us to explore relationships between movement and context. And it would be a great tool for us to interpret our results and communicate the results to our collaborators from other domains as well. So because of the importance of visualization, we've seen a trend of increasing different papers on visualization in the area of movement and visualization of flows. So there's no surprise that following the revolution in our data and access to a lot of data sets, we see this trend happening. So together with my PhD student, we looked at the trend over the past 10 years. And as you can see see the citation of topics on visual analytics of movement is growing very rapidly. We looked at different characteristics of these papers and visualization techniques, and we tried to come up with the different classes of visualization methods, and using different elements in terms of visual elements such as vector or raster representation, aggregate or discrete movement, and as well as functional elements such as the ones that you have the cartographic cube, like interactivity, knowledge construction. We try to classify the existing paper on visualization of movement. As you can see, we found 3 clusters that we could identify for interactive visualization of aggregate movement flows. Cluster 2 represent communicative visualization methods to map aggregate movement, and cluster 3 represent papers on exploratory and dynamic visualization of trajectories. So basically, this graph shows that most work have focused mainly on aggregate flows, and although we have some papers on discrete trajectories, we see less interactive and exploratory tools on discrete trajectories. These are just 40 papers of 150 papers that we reviewed, but we see more visualization that incorporate movement parameters and less visualizations of context parameters and contextual information of movement. More visualization provide a static view of movement and aggregate flows, and we have less dynamic visualization, although we see a trend in industry moving towards more dynamic representations. So although visual analytics are advancing and we see a lot of work in this area, we find that there is a rigidity in visual analytics that the representation cannot be changed by the user. So it would be helpful for future work to basically look at ways in which we can expand the flexibility of our tools and let the user decide how to represent flows and movement trajectories. So therefore, more interactivity and more flexibility in future visualizations would be important if we want to move towards a human-centered data science for movement. And also, it is important to have a general framework that we can use to assess the usability of our studies and evaluate different visualization techniques for a better representation of movement in a space and time. So with that, I would like to invite you to a workshop that we are organizing in Geoscience next year. Because of COVID, we had to move it to next year, but that would be a great lead from this workshop to the next, that we focus on visualization here, and next we're going to bring visualization and analytics together for advancing movement data science. I would like to invite you to contribute to our workshop. This has been a tradition in GI science that we bring together people from GI science, computer science, domain experts to work together on different trends happening on data analytics of movement, data-driven and theory-driven methods for studying movement. And it would be great to bring visualization community in these workshops as well. So with that, I would like to once again thank to our previous speakers and the keynote speaker, as well as you for taking the time to see our workshop, and also the program committee put a lot of work for us here to review the papers and make this and help us to make this workshop happen. I would like to hand over to Alan for his closing remarks, but I hope you enjoyed this workshop and I hope you enjoyed the rest of your conference. And I hope to see you soon in person in future venues. Thank you so much. And Alan, the floor is to you.
Okay, I don't have any slides, so I guess
I stopped sharing here.
Stop sharing. So thanks for everybody for participating today. I think it's been a fairly exciting workshop in spite of all of our remote locations and technology issues and all that sort of thing. I'll keep this kind of short because I think we're at the time we said we were going to be already. But I want to start by, I don't think Jeremy's still online, but I want to thank him for doing that keynote. He hit on a number of things I was thinking about talking about in my closing remarks, so that makes my closing remarks somewhat shorter. One of the things that struck me was that across all of, we had quite a bit of variety today. Across all of our different presentations today, there were quite a different number of kinds of phenomena and kinds of data that people were looking at. Trajectories was the main thing, but then there was also origin destination data that in some cases is quite different than trajectories because it often starts with aggregated data rather than actual movement along a track. We had a little bit from Jeremy on movement of fields with his glacier example, the ice flows and so forth, but we didn't have too much on that. We had a couple of different people talking about the interactions between social networks and geographic places and the kinds of complex movement you have in both geographic and social space and the challenge we have in trying to intersect those two. And we had some attention to events, which are more complex kinds of phenomena that have both geographic movement and other things that we might use the term movement to describe that's non-geographic. One of the things that struck me about all this is that we've been working with visualizing movement for more than a century, and we're still dealing with some rather primitive ways of representing movement, I think. Some of them are becoming quite elegant in terms of what they look like on our displays, but I think it might be worth our while to start thinking a little bit more creatively about how to represent movement visually. We have a lot of attempts to do various kinds of traces, either along actual paths or the non-planar movement that we heard in one of the last presentations from Clio's group. And then we have some examples in the workshop of abstract representations. The donut representation was one that comes to mind there as well. But there's probably a lot we can do by borrowing from the InfoVis community more for some of the more abstract kinds of representations and figure out how we can repurpose those to represent some of the more complex characteristics of movement data rather than just the flow and just the trajectory, so that we can get some better insights out of the data. I'll close with just a couple of ideas for areas that I think it might be worth us looking at trying to push the field a little bit, some new, maybe not new directions, but directions to push a little bit harder. One is, and Jeremy's talk addressed this a little bit, we're still finding challenges with data that are not consistent and precise. Things like the human migration data, humanitarian relief kinds of migration and so forth. Those are very messy sorts of data. It's difficult to figure out how to deal with all the different levels of uncertainty in those data. And I think there's quite a bit we could do with looking at how do we deal with messy movement data rather than the precise data that we get from GPS or even from Twitter. Second thing is looking at strategies to represent complex interactions between human behavior in the world and human behavior in social networks. We had a couple of people talking about those kinds of challenges today of how do you intersect social network and movement in that abstract social space with geographic movement in real space. we're still not very far along, I don't think, in terms of how we represent that visually. Third thing, and Somayeh dealt with this a bit in her closing comments as well, is intersecting more with the visual analytics community and thinking about ways that we can go a little bit farther in getting the human in the loop earlier in interacting with our computational methods that we're using to process, particularly the larger data set, movement data sets that we have, and when we're trying to model and do predictive analysis and so forth, getting the human earlier in the loop through visual interfaces to steer that movement modeling kind of work. And then one thing that we didn't hear anything about really today to speak of, or maybe not at all, was, and this is kind of my favorite, is, and some of you may know, I've been working over the last few years on movement in language. How do people talk about movement, and how do we extract movement from statements that people make? And I think that's a quite rich area to find a very different kind of data set that has a lot of movement information in it that we're not currently leveraging very well. One can think, for example, of scientific documents where there are maybe centuries of description of animal movement that could be connected with our more current GPS kinds of data in that domain. And how do we actually extract that kind of data? But then when we extract it, how do we visualize data like that? And that gets me back to my first topic, I guess, of visualizing messy kinds of movement data. So I'll leave it there and turn it back to Clio, I think, who started us off, maybe to close things out.
Thank you, Alan. Talking about future goals is the best way to close this up. I'd like to thank all of our speakers. Thanks to Alan and Somayeh for helping organize this as co-organizers, and to wonderful help from IEEE. And for our technician here, we just owe her a huge round of applause as well. And we hope to do this again in the future as well. You guys have a great day.
Thanks, guys.
Bye.
Bye. Thank you all.
Program developers spend significant time on optimizing and tuning applications. But working with binary code to understand what compiler optimizations were applied can be challenging. We present our visual analytics system, CCNAV, designed to identify and assess compiler optimizations in binary code. Check out our paper to learn more.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
Suppose you want to see the overall commit structure of a new project repository. Using Git client tools, GitHub Network, or Git log command is quite burdensome to get overview and navigate data. We presented Graser as an interactive visual analytics system for the Git metadata to help users explore and understand the context of development history.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained datapath extraction method, a river-based visualization, and a contribution analysis method.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
We present transfers,
a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIV matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user-selected path to justify and reason the AD analysis.
Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
CarxS is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and exposed through our Morse-Mel complex guided semi-automatic tracing tool. The topological ridge graph underlying our MSC guided tool is robust against gaps in the signal.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heat map view shows the stability of the selected region and provides region adjustment by directly clicking.
Reservis is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration The confluence of explanatory and exploratory visualization can be applied to visualization in public spaces.
We demonstrate that people can use the spatial cues available in virtual reality to help them effectively remember and recall scholarly articles. We used a virtual coffee shop and asked participants to remember 4 abstracts from scientific publications, and we termed this method a virtual reality memory palace variant.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
Asteroids have always been and will always be a threat to life on Earth.
Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
The success of a convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the thinking model is not easy to understand. We introduced the Explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural network. Using the Explainer, users can progressively explore the thinking model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
We present Strat-Graphics, an approach for designing data-agnostic and fully reusable visualization templates. Strat-Graphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
If machine learning were like education, we would like to test what concepts our student, the model, has learned. Has it learned the concept of object rotation? Does additional text help with object recognition? We need a methodology and platform for conducting such tests. In this paper, we present a novel visual analytics tool that enables hypothesis-based evaluation of machine learned models.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
Attention mechanisms have greatly improved the performance of many language models. Yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
As data is changing, our understanding of data should be updated correspondingly. Based on machine learning approaches, we formulate a drift-level index to monitor the evolution of multi-source data, which allows users to capture and reason significant changes from time series data. The proposed visual analytics system is called Concept Explorer. More details can be found in our talk.
Linking and brushing is very useful for interactive visual data exploration. Data-driven brushing tools are getting popular recently and achieve good results, for example the MoVIS brush and the CNN-based brush. However, these brushing tools are optimized by the data from a large number of users, which are not suitable for everyone. In this paper, we introduce an adaptive brush model which takes the user in a loop to improve the brushing accuracy.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
Serine graphs are variants of stack graphs with curve-based line, and the main factor affecting its readability is the sign allurance through a perceptual inconsistency of the orthogonal and vertical direction. Aiming at reducing its impacts, we revisited the baseline formulation and proposed the concept of composition to help the serine graph layout optimization. The result shows that our algorithms perform better than the others.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
Taylor-Coyer flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
In our paper, we address the problem of navigating complex multiscale and dense environments, such as these molecular models. We present a technique for browsing a model by clicking on textual labels, which we call hyperlabels. This allows the user to intuitively navigate the hierarchical organization of the model. For more details, read our paper or watch the talk.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
The classifier trained on the historical data may fail to classify the incoming data when the data distribution is changing. This phenomenon is called concept drift.